Hello, everybody. Welcome to EEE 135 Renewable Energy Systems, Chapter 10, Geothermal Sources. This is the second lecture of the week. So last time we talked about all the different types of geothermal sources underground. We talked about the different type of plant designs for electric generation. Today we're going to talk about the low temperature applications, meaning what can we do with geothermal sources besides making electric energy, and how to go around doing that. So first thing is, what can we use low temperature application for? It's not electric energy. So here's kind of a list. Number one, space heating. So just heating your room. Space cooling as well. In the summer, you could cool your house down. Melting snow on pavement, walkways, roads, bridges, right? We could pump geothermal heat into the actual concrete through pipes, and that will melt the snow. Greenhouse temperature control. So if you have a greenhouse, you could, again, pump heat from underground into the greenhouse to keep a steady temperature. Aquaculture temperature control. Aquaculture is basically fish farms or any type of body water meant to produce fish or animals. So again, a lot of fish like to have the water pretty constant temperature, and if you have it on the surface in the winter, it could vary a lot. So pumping geothermal heat into the fish tank or the lake or pond will help stabilize that temperature to grow the fish as fast as possible. Hot springs for resorts is another one. So you might just have a naturally occurring crack in the ground where you have some heat coming out and there's a lake or small pond. You could turn that into a hot spring resort where people could go take a bath in it. The hot water is very relaxing. It's kind of like a natural jacuzzi type of thing. So there's lots of hotels and spas for specifically that. Lastly, you can use heat pumps for individual houses. So when you build a house, you can install a heat pump. In certain areas, you could dig underground, put some piping, and use that as part of your HVAC system to control the temperature in your house. So we'll go through each one, kind of give you some more details on it. So first thing, space heating. So basically, you build a house on top of a low temperature geothermal site, and you harness the heat. You take, during construction of the house, you would drill down into, I don't know, 50 feet underground, let's say, maybe 20 meters or so, maybe a little more, 50 feet. And then you can put some pipings in there, and it'll be warmer underground than it is in your house whenever it's in wintertime, and you could pump the heat into your house, right? The heat pump will literally be a pump that will pump water to circulate heat from, we'll have the warm water in the geothermal source will come into your house. It'll cool off because your house is colder, and the cold water out of the heat pump will go back into the geothermal site, and it'll continuously pump this, and then heat will always be coming into your house from underground. Okay. So basically, you drill pipes to the geothermal site, grounding heat to your HVAC heater and or hot water heater. So you can also use it for hot water heating as well. All right. Space cooling is basically the same type of ground geothermal heat pump, except things are working in reverse. You can reverse the flow of liquid and pressure to dissipate extra heat into the ground. So remember, in the summer, you might have 100 degrees Fahrenheit air temperature, but in the ground, it'll be more like 50 or 60 degrees Fahrenheit. So you could take the heat from your house, maybe it's like 80 degrees in your house, you could pump it into the ground and absorb the heat, and you might get like 65 degree Fahrenheit water coming back, and you could slowly try to control the heat in your house. You probably won't be able to get it to like 70 or 69 degrees, but you could definitely get it closer to the 80 degree range than letting your house turn to 90 degrees something, right? So it's not meant to completely take over the entire air conditioning system, but think of this as a side system that can assist in keeping your house warm or cold. Okay. Some people are okay with 80 degree Fahrenheit in the house. Some people can't go past 70 degrees. So depending on the people, but there's a place and time for these type of things. I personally think the heat pump is amazing. If I ever buy a house, I definitely want to see the heat pump with it. It's very efficient, and it does wonders. So that's space heating and cooling. Next thing we have is melting in the snow. So we don't really get it here in California, but more in the northern areas, you might have snow or rain. It's cold, it might freeze up, and you'll have slick ice on the pavement or just too much snow. Can't really drive a car on top of that. So a lot of times, busy intersections or walkways, you put heaters underneath the pavement to actually get rid of the snow. You can even install that in your house. If you have a driveway, you could pay extra money and put heating pipes in the actual concrete, and that way you never have to shovel snow every morning. So instead of using electricity or gas to burn to create heat, you can use a geothermal source instead. So basically, we can melt the snow and cool the road by transferring geothermal heat to the road pavement or to remove extra heat in the summer. It works both ways. So let's say it's winter and you have a bunch of snow in this pavement, right? Actually, it's the right-hand side. So here on the right-hand side, you got a bunch of snow in the pavement. Remember, down in the earth, we have a near constant about 60 degrees Fahrenheit temperature. If it's 30 degrees up here, we could pump 60-degree Fahrenheit liquid into a heat exchanger, and the heat exchanger will then transfer that 60 degrees Fahrenheit to the pavement, and it'll raise it above 20 or 30 degrees, which is what the air probably is because it's snowing, and you'll melt the ice. Right? You're not going to get this thing to like 80 degrees or something crazy like that, but you'll definitely get it above the melting point, above the freezing point of water and melt the snow. So, and this is a system people use a lot, right? If you're in an area that's willing to put the money to build this, it works. Conversely, in the summer, the pavement might get to like 150 degrees Fahrenheit or something crazy hot like that. It's not that good to walk on. You start melting things. You can do the same idea where, remember, inside the soil was 60 degrees Fahrenheit. So if we have 150 degree pavement, we could then take that heat, put it into a heat exchanger, and then transfer that to the soil, and the soil will absorb some of that heat and return cold water back into the heat exchanger, and that will cool the pavement down. So again, geothermal sites are always like a giant sponge that wants to keep a 60 degrees Fahrenheit temperature. And whatever is outside, it'll try to absorb heat or give off heat to try to keep that temperature as steady as possible. So we could use this as a way to just level off any crazy temperature variations during the day or week. Okay, so summer it cools down the road. In the winter it melts the snow. I mean, it sounds good both ways, right? One question is, why do we use a heat exchanger? Why can't we just directly pipe the water in the soil directly to the pavement? Well, when the water in geothermal source, it could be corrosive. Remember, sometimes you might have some corrosive brine, salt water, or some other minerals, elements in there. You don't want to directly put it into pavement because pavement is asphalt. You could corrode it. You ever wonder why you're driving, you got roads that are breaking down and bumpy and potholes everywhere? That's because pavement breaks down a lot, and if you start pumping corrosive liquid through the pavement, you're going to accelerate the road breaking down. We don't want to do that. So like a binary cycle plant, let's have two complete separate liquid looping systems so we don't transfer that corrosive material to the pavement, right? The piping and the heat exchanger we could build tough enough to withstand the corrosiveness and let the pavement do its thing of supporting the road and the cars and all that stuff, okay? So yeah, melting snow, and this thing typically happens in the north, right? All right, another one is greenhouse. So greenhouse, we try to grow plants in it. One big thing about greenhouse is it captures the sunlight to try to keep a constant temperature for the plants to grow. But in the wintertime, it gets cold, and a lot of greenhouses have to have really big heaters, and it's a very expensive electric bill to keep the greenhouses active in the correct temperature during the winter. So what some people realize is, again, we could use a geothermal source underneath the greenhouse and put some pipes to pump in some hot or warm water into that greenhouse, have some pipings and radiators everywhere, so we could take that warm-ish temperature water and dissipate into the greenhouse to keep the greenhouse from freezing over, right? And then once it releases its temperature, the liquid releases its heat into the greenhouse, it'll get cold, and you pump it back into the ground to reheat again. Okay. So in the wintertime, the geothermal source will heat up the greenhouse. In the summer, where it gets too hot, normally we have to run air conditioners. Again, that costs electricity. We could instead have radiators with pipes to absorb the heat, pump it into the geothermal site. It'll take the heat and absorb it and return colder water, and that will cool down the inside of the greenhouse. Okay. During the winter, how do we keep the greenhouse warm? You pump water from warmer underground geothermal source into the actual greenhouse, and the summer is the opposite. So again, you can see this is the geothermal source is trying to keep the temperature steady at the greenhouse. Okay. So aquaculture, same idea, is we got a giant pool of water. It needs to be constant temperature, right? The geothermal energy can help stabilize the water temperature in a fish farm all year round by pumping the heat into it. So the exact same setup as greenhouse effect. Put that piping everywhere, get some water pumps going, some radiator fins, and then you'll have a free source of energy, right? It's a good idea. Next, we got hot spring spa resorts. So this is kind of a picture of a small building where it's a bath. It's an open public bath, and you can see people hanging out there. And even in the wintertime, this thing is almost not boiling hot, but it's probably like at least 100 degrees Fahrenheit, if not more. And it's really relaxing because, it's the warm water. So people say it's supposed to make your skin last longer, give you more life, blah, 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 right? In Japan, this is really popular. I went to Japan and went to a couple of these throughout my life. And it's very popular, but it's very location dependent, right? The only reason why this thing exists here is because there's a crack in the earth and there's geothermal heat literally rising through the crack to heat the water. So this water is pretty much going into the crack to get heated and coming back out. And it's constantly circulating to keep this temperature really high despite it snowing everywhere. Okay. Hot springs are popular relaxation areas. Allows the water to stay hot during the winter. Geothermal sources has a crack to surface pond and continuously releases the heat, right? And as long as the geothermal site's active, it's going to do this all year long, right? What are the geological limitations of building hot spring spas? It only works if the geothermal source is very close to the surface. It has to naturally occur. I suppose you could drill and force a crack into it and make artificial ones, but all the spas I've seen are naturally occurring, and they build a hotel on top of it, and then they invite you to come over there. So a lot of times these are kind of in remote areas in the mountain that you have to kind of travel to or get an escort to get there. You won't see this like a Hampton Inn where it's like every 10 or 5 exits, there's a Hampton Inn, right? It's only very select remote areas in the mountainside you'll see these. But they're pretty popular, right? Especially among the older crowd, right? I see a lot of grandma and grandpas go there because the idea it's supposed to relax your body, your joints get looser, and then it's supposed to help with arthritis and make you live longer and this type of stuff. Okay. So last one is heat pumps. So what is a conventional heat pump? This is a system that can move heat from one area to another using basic refrigeration cycles. It's basically like your air conditioner, how it cools your house down. You can kind of do the opposite of AC and heat your house, right? As long as there's another source outside your house, you can pull heat from there and bring it into your house, okay? There's alternative to these conventional heat pumps. Well, I would say the one thing with this conventional heat pump, it takes electricity, right? You have a compressor, you got water pumps, so there's a continual amount of electricity needed to keep this running. An alternative to using a refrigeration cycle is using a closed loop horizontal system, a closed loop vertical system. And these are basically, you have the heat pump where you put a bunch of pipes into the ground. Do you want to layer it flat on the ground underneath? That's horizontal. Or do you want to layer deep vertically where the pipes go down, right? And there's pros and cons for both of these. Another thing you could do is you can have a closed loop system where the liquid in a geothermal heat pump will go to a lake nearby, and the lake will dissipate the heat for you, right? Because you have a large enough lake, the lake's going to want to stay at a cool temperature throughout the whole day. And then you could use that to balance out the temperature in your house. Lastly, you have an open loop system to where you have a bunch of water underground in your house. So you just happen to build your house on top of like an aquifer or a well. And you could just pump the well water into your house because it's going to be cold and you'll cool your house down. Or in the winter, it's going to be warm relative to the temperature outside and you can heat your house. So, but the big thing is open loop means it's not the same water getting pushed through. You're taking literally the well water and continuously cycling through the house. That's the open part. Okay. So we'll go through each one of these. First, we're going to mainly focus on the conventional heat pump because this is by far the most complicated one. This is also the most common one because a lot of houses, especially fancier houses now, are going to have a heat pump in their house. So you'll probably see one and then you might have to know something whenever it breaks down. Okay. So first I would say with a conventional heat pump, you do not need a geothermal site for this. This is your standard AC unit outside your house. As long as you have a coil outside and a coil inside in your attic, you can use a heat pump. Okay. A lot of times when you buy your HVAC system, you can opt to get a fancier one with an additional heat pump in parallel with your standard AC system because the heat pumps are more efficient than your regular AC system to use. All right, let's see how this works. So you're going to have a compressor, and then you got two coils, a condenser, an evaporator, and expansion valve. Those are the four pieces. And your main goal is to pump liquid through this whole loop over and over and over again. The main device that takes energy is a compressor. It's hard to compress liquid. It takes a lot of effort. So the big power draw is this compressor forcing liquid where it doesn't want to be. But once you force it in the system, it'll work naturally and cool your house down. Okay. So the 4 steps is number 1, we'll start with the compressor right here. The compressor will force the low pressure vapor into high pressure vapor. So coming out of the system, this blue, this is your low pressure vapor. And a vapor is called refrigerant. It's not just water, it's a special type of liquid. Okay. The compressor pulls it from the system and then pumps it into the condenser. So this whole red pipe and this condenser out here is high pressure because of the compressor forcing it. Okay. So you have high pressure liquid or vapor going into the condenser. Now the condenser is honestly just a heat exchanger. Remember what we said heat exchangers are? They transfer heat to something else. So you have pretty high pressure vapor here. It's coming in. It's going to be very hot. Air outside your house is going to, you have a big fan pushing air through the heat exchanger, okay? So the condenser would take the heat from the high pressure vapor because you got wind rushing through the coils, the big fan's pushing the wind through it, and instead of being like 200 degrees Fahrenheit, it'll go down to like 100 degrees Fahrenheit. I don't know exact numbers, but you're going to lower the temperature because wind is rushing through and taking the heat out into the ambient air. As the heat leaves, the vapor will turn into liquid, right? Remember the whole, just like with steam, it has a lot of energy. When you take heat out, the steam turns to liquid. Same thing here. The refrigerants in vapor form, it will turn to liquid. Once it's in liquid form, it'll still get pushed through the system out the condenser. So now we kind of have this high pressure liquid. So work's already been done. We took heat out the system. Okay, sorry. Now, number 3 is this liquid is going to hit the expansion valve. The expansion valve is nothing more than like a nozzle, a spray nozzle. That's it. Okay. It will take the liquid and spray it into a mist, just like a spray bottle. Right. And there's a lot of force behind this because the expansion valve is a very, very tiny little pinhole, and it'll spray it out into mist. So coming out of this is you're going to have low pressure vapor. Mist, sorry, right? And then this will come out and go into the evaporator core, and then this will then cool down your house. Okay. So coming out the expansion valve right here, because you had high pressure vapor, you spray it. One big thing you're doing is you're increasing the volume. right? So typically think of a small pipe with a lot of pressure. You have a very small pin that you're only letting a little bit of liquid through, and you're suddenly increasing the volume. So if you increase the volume, then the temperature's gonna go down drastically. So between these 2 points, you'll get a big drop in temperature. So this liquid right here, the mist coming out, this is gonna be really, really cold, like less than 0 degrees Fahrenheit, probably. Very, very cold. And that's where we're gonna go to another heat exchanger, number 4, where the evaporator has that really, really cold mist. And then it's gonna come out into your house and it's gonna absorb the heat. So if I have a heat exchanger at 0 degrees Fahrenheit and it's running 80 degrees Fahrenheit air in your house, it's gonna absorb 80 degrees and it's gonna come out maybe 60, 55 degrees Fahrenheit, and that's what you're gonna get in your fan vent, okay? So number 4, the evaporator core will absorb the heat and turn the low pressure vapor into liquid form again. And now that's right here, you got the liquid, it's gonna go back through here. Accumulate is just kind of an area in case you have extra, and then it goes back into the compressor. So those are 4 stages. Compressor makes high pressure vapor and it's really, really hot. The condenser cools it down to a mediocre heat. And this is where a lot of work is done. So we lose a lot of heat coming out here, goes down through the expansion valve, it mists out, it creates mist that's freezing cold, and then it cools your house down, and now you have lukewarm vapor, and that goes in and gets pumped again. So it's just literally, it's a process that goes over and over and over again. Remember, 2 cores. Outside core gets rid of heat, inside core absorbs the heat. So you're just taking the heat inside your house through the liquid, passing it outside to the condenser core. That's all you're doing. And then the liquid or the vapor, that's a medium of taking your heat in your house and throwing it outside. And the compressor is what makes the whole liquid loop flow. So, I mean, that's what HVAC in a nutshell is. All right, I just want to interrupt the lecture real quick because I wrote an error. So I just want to fix it right now before you guys go any forward. So here, we're talking about the conventional heat pump cooling cycle. Number 3, it should be expansion valve sprays high pressure liquid into mist and turns it into low pressure liquid, not vapor. Okay, and then that's about right here, expansion valve. And then number 4, we go to the evaporated core here, and this will absorb the heat and turn the low pressure liquid, which we just had, into low pressure vapor. I believe it was swapped over here before. So I just wanted to interject just to make sure that we catch this before we go any further. The rest of the explanation should be okay on the next heat cycle. So thank you. Reverse the direction of the fluid and we could heat your house. Okay, so let's try this now. So we have the same compressor. The compressor is pulling in the low pressure vapor. So this is like kind of lukewarm, not a lot of energy, low pressure. It's in vapor form. It goes to the compressor and it pumps it really, really hard and pressurizes it. So the compressor will force low pressure vapor into high pressure vapor. High pressure vapor here is very hot. Okay, I guess I should say, why does low pressure vapor turn in increased heat when it goes to high pressure vapor? You remember that PV equals nRT, right? There's a ratio of, if you have any type of vapor and you pressurize it and you force it into a smaller container, the temperature will naturally go up. Okay, so because I'm pressurizing something, temperature spikes. Okay, now it took a lot of work to pressurize it, that's what a compressor does, but it creates a lot of heat, right? And that heat is then used in our house. So right now, this exchanger, the condenser is in our house. This thing might be 150 degrees Fahrenheit. So we have a cold air go through the heat exchanger and the warm air comes out. That could be 100 degrees Fahrenheit and heat your house. Okay. So high pressure vapor goes in, it warms your house up, and then the condenser will releases the heat from the high pressure vapor and it turns into high pressure liquid. So we're losing that heat. The vapor will then naturally turn into liquid because the temperature is getting lower. Okay. So we got the lukewarm high pressure liquid come into expansion valve. The work's already done. The expansion valve will do the same thing. It sprays the mist. So spray into a mist, the high pressure liquid will turn into low pressure vapor. Or liquid, sorry. Right? So let me backtrack. So you have high pressure liquid, expansion valve, it missed out. Yep, you'll get into low pressure liquid here. You'll go into so that's number 3. Number 4 will go to the evaporator core, and the evaporator core will be outside in your house, and you're going to have to dump the cold air and try to get a little bit of the warm air back in. Okay, so you got to remember, we said when it comes out the expansion valve, this temperature is like 0 degrees Fahrenheit, freezing cold. Okay, you get 0 degree Fahrenheit comes at the evaporator core outside your house. Now, outside your house, it's cold, but it's not 0 degrees Fahrenheit cold, right? If my liquid is 0 degrees Fahrenheit, but my outside temperature is 50 degrees Fahrenheit, that's a big difference. To us, cold is cold, but to the heat exchanger, I could take 0 degrees Fahrenheit and 50 degrees Fahrenheit, and I could pull 0 degrees up to maybe like 30 or 40, right? And that's the idea, is the evaporator core will take the 50 degree Fahrenheit heat and absorb it into the system, and now coming out, you got lukewarm, low pressure vapor that goes back into the compressor. Okay, so it's the same idea, except everything is working reverse, where now we're taking heat from the outside and pushing it into our house. Now, I know the weirdest thing you're going to say is, how is 50 degree Fahrenheit considered heat whenever we want 100 degrees Fahrenheit in our house? When we say heat, it's relative to the liquid, not to us. Okay. Remember, this liquid coming in is 0 degrees Fahrenheit and outside 50 degrees Fahrenheit. To the system, 50 degrees is hot, and it'll absorb the heat. Okay. We'll carry the heat over, compress it, and kind of do a slingshot effect to get 150 degrees Fahrenheit heat. And from inside our house, 150 degrees inside the core is much hotter than maybe 75 or 76 in our house. So it will release heat again. Okay? And that's a system. It's a closed loop system. It will keep moving forever as long as you're powering the compressor. Okay? So that's your conventional heat pump. Is really, really good. People like it a lot. Oh, I guess one thing I would say, right here in the middle, this is a reversing valve. So notice that this is like a check valve that you have to flip back and forth to tell the compressor which way the liquid should go. Notice that the red liquid is going to the right, to the heat exchanger or the condenser in heating cycle. If you go up, notice that the red liquid, the really hot vapor, is going to the opposite core, the condenser outside. Okay, so the only difference between cooling and heating cycle of the heat pump is which way is the compressor pushing the liquid, right? Is it pushing it to one core or another? Okay, that's it. So that's your traditional heat pump. Welcome to kind of a sideshow of HVAC, but I think it's very important to know these type of things. We'll use the idea of the heat pump later on in this lecture to talk about the geothermal version of it. Now, anytime we're talking about heat pumps, the question you always got to ask yourself, is it worth having a heat pump, right? It always goes down to dollars and cents. Because I can always take electricity and run it through a resistor to create heat. It's inefficient, it's expensive, but I can always do that. 2, I can always burn wood, or I can burn natural gas. I always have these options. I have a fireplace, right? We have other heaters. So we got to ask ourselves, is a heat pump more efficient than burning wood? If it is, we use it. If it's not, we should never use it. The way we could quantify this is called the efficiency of a heat pump, right? It's called a coefficient of performance. So C of P is always equal to the heat delivered to the house divided by the energy supplied to the heat pump itself. Okay? The compressor takes so much energy to use. We get so much heat out in the house. This needs to be a high ratio for it to be effective. Otherwise, I should do something else. Okay. Note that the efficiency heat pump is not a static number by a device. It changes based on the outside temperature. Okay. So depends on the temperature outside your house, this could be higher efficiency or lower efficiency. Okay. For example, if the temperature is less than 32 degrees Fahrenheit, basically is below freezing, the COP is 1, meaning the amount of energy you're putting in electrically to the compressor is equal to the same amount of heating you're getting out. You're not getting any benefit. It's not efficient anymore. You're better off taking electricity and just burning it through a resistor to heat your house, or burning light bulbs to heat your house or something else, right? So the COP should be well above 1 to be efficient, okay? So what should we do if the COP is equal to 1 or lower? You might as well just turn off the heat pump and use something else. Use resistive heating. Now, when you have a heat pump installed in your house, you will actually have 2 heaters. The heat pump itself, which is a standard operation, and you're going to have what we call auxiliary heating, or some people call it emergency heating. These are the big power resistors I'm talking about, because there will be a chance that your heat pump is going to not work in sub 32 degrees freezing temperature. So this is where that resistor emergency heating kicks on and your heat pump kicks off, right? It's probably pretty rare to use it here in Turlock, but maybe once or twice a year in central or northern, where you guys are in Sacramento. You might have a couple of days out of the year you'll have below freezing temperature. You want to have this auxiliary heating just in case. Okay. So how do we calculate it? Let's do a quick example. The heat pump efficiency. We have a heat pump that consumes 7 kilowatt hours of electrical power and delivers 60,000 BTU of home heating. What's your coefficient of performance? Now remember, BTUs and kilowatt hours are both energies, but you need to convert them. And the conversion rate is always 1 kilowatt hour is equal to 3,413 BTUs. So there's 2 ways. You can either convert everything to BTUs or convert everything to kilowatt hours. Being an electrical engineer, I like kilowatt hours more than BTUs, so I convert it to kilowatt hours. So 60,000 BTUs divided by 3,413 BTUs, it would equal the amount of kilowatt hours. You do the number crunching, you get 17.58 kilowatt hours. Okay. So that's how much heating we're doing. Now let's calculate the COP. We got the heating into our home of 17.58 kilowatt hours, but the compressor took 7 kilowatt hours to operate. So our total gain is 2.51. So meaning I put in 7 kilowatt hours electric energy, I got 250% return, or I got an extra 150% on top of what I used as home heating. So this is a decent system because I'm getting free energy per se, or free heating per se. Okay. So FYI, COP of 5 is considered very efficient. COP of 1 or lower means turn off the system. Okay, so that's kind of the ranges you're looking at. Okay. So this is where we're going to take a 15 to 20 minute break. We're going to have an exercise where you're going to calculate heat pump efficiency. So we have a heat pump that produces 120,000 BTU per hour. Okay, so we're talking about power, not energy. So 120,000 BTU per hour. The equipment rating for the heat pump is shown on the side. Calculate this coefficient of performance. Okay, so I kind of threw a little bone in here. What's that per hour mean? I'll let you guys figure it out. Okay, the whole the whole heat pump system has a water pump of 2 kilowatts, a compressor of 4 kilowatts, and the fan systems of 1.5 kilowatts. So you figure out how you convert kilowatts to hour usage, and you got 120,000 BTU per hour. Just make sure the units line up, calculate coefficient performance. We'll come back and check your answers. Okay, so good luck. Let me know if you need anything. We'll see you in a little bit. All right, welcome back for our 15-minute break for second lecture, geothermal sources. Talked about looking at the heat pump efficiency. So let's go ahead and see how we did this. All right, so first thing, we have 120,000 BTUs. So we convert that to kilowatt hours. So we have, take 120,000 divided by 3,413, we get 35.16 kilowatt hours. Total equipment power, put everything together, you get 2 kilowatts plus 4 plus 3, 1.5 kilowatt hours. So we get 7.5 kilowatts. We use this for 1 hour to produce 120,000 BTUs per hour. So 1 hour of running system gives us 120,000 BTUs. 1 hour of using the system gives us 7.5 kilowatt times 1 hour, or 7.5 kilowatt hours. Okay, so both of them are now in terms of energy. So COP is going to be equal to the output of 35.16 kilowatt hours worth of heat divided by 7.5 kilowatt hours electric energy we put into the system. So we get an overall coefficient of performance of 4.69. This is really good because that means we almost quadrupled our energy by using a heat pump versus just using resistors to heat our homes. Okay. So heat pumps, if you get this high, definitely really good. Install them, save a decent amount of money on electricity bill every month. All right. Next one we talk about is let's talk about the geothermal sources and how they could play into using heat pumps to heat our homes or offices. We're getting away from all the refrigerant cycles and all that stuff. This is more just putting a bunch of pipes in the ground and absorbing the heat, right? So what are the land requirements for this heat pump type of systems? We need a large square patch of land. So horizontal means the pipes are getting laid flat on the ground, maybe, I don't know, a couple meters below the surface, okay? So you dig up a big patch, put the pipes and put dirt on it, plant some grass, and you're done, okay? You roughly need 2,500 square feet per 1 ton of cooling. So 1 ton of cooling is 12,000 BTUs per hour. You probably heard this before you ever look at HVA systems. So I forgot what the numbers are, but I think a house, you probably want 1 ton of cooling per 1,000 square feet, I recall. Could be off on that a little bit. So let's say you have a pretty big 2,000 square foot house, you would at least need a 2-ton system. So if you're going to use this type of heat pump or closed loop horizontal system, you're going to need 2 tons of cooling. So you're going to need 5,000 square feet of land to put these pipes on. So that's a pretty big backyard, right? And then you'll have enough for your house. Okay. How deep do we build this piping system? You won't build it below the frost line of the ground. So whenever it freezes over, there's a certain distance into the ground where the cold won't reach and you won't freeze any of the water. That's called a frost line. So I don't know what it is here in California, but it's probably like 5, maybe 10 feet underground is what you expect. Probably not even 10 feet. I'll probably more like 5 or 6 feet, right? So just dig 5 feet, put your pipes, fill it back up with dirt. In the winter, it should not freeze over because the ground insulates the piping from the cold weather up top, okay? And just remember now, we're in the ground. There's no geothermal heat here. You're just using the ground being that constant 50 or 50 degree Fahrenheit temperature to run a heat pump. Okay, remember we have 50 degrees Fahrenheit here, and inside your house is 40 degrees. You could heat up your house a little bit. Okay. All right. Or if you want, you could go back to using a refrigerant system like we talked about earlier. And then you could use this 50 degrees Fahrenheit as one of the cores here. And in your house, you could have a little higher heat source there too. Okay. But the big trick here is put in a pipe horizontally. One reason why you use this is you don't want to dig too deep. Maybe, you know, if you live in Folsom per se, Folsom used to be a strip mine, right? So you dig more than 4 or 5 feet in Folsom, you're going to hit nothing but rock. And you're not going to go further than rock. It's really hard to go past that. So this is where you use a system like that. We have a very shallow dirt layer. Okay. A closed loop vertical system is kind of the opposite in the sense that you're taking out the pipes and putting them vertically into the ground. So you're having a very narrow strip of land, but you're drilling really deep, like 50 or 100 feet deep to put the pipes. Okay. So what are the land requirements for this type of heat pump system? You want a small vertical strip of land. So basically, if you don't have a lot of land because your lot's really small, this might be a better system if you can dig deep easily. Okay. How deep do we want to build these piping systems? Drill set of pipes typically down 30 meters to 120 meters. So 30 meters is roughly 100 feet, and this is more like 400 feet. Okay, so that's pretty darn deep. So just if you're willing to drill down deep and put the pipes, it's a very compact system from a surface level, and you can get some really cool. You can get some really constant temperatures here to make your system run pretty well. Okay. If you can't do any of that, another version of this is a closed loop system with open water source. So let's say you have a complex here and you have a big open, medium-sized lake. Some people put a lake so that makes it look nice or other things. A lot of times you put a lake nearby because the water is always a good way to keep the temperature constant. We talked about this in the previous chapters, is water tends to hold temperatures more constant than land. So it's like a sponge where it'll, if it's too hot, the water will be cooler. If it suddenly turns really cold, the water will be warmer than the outside air. Okay, so it helps make the temperature constant. Excuse me. And we could use that similar to the geothermal low temperature or just the underground constant temperature of the previous ones. Remember, we said it's roughly 50 degrees Fahrenheit. The lake is probably the same. Okay, so what are the land requirements of this type of heat pump systems? You can have a body of water nearby, either man-made or artificial. It needs to be big enough to heat energy for the building. Can't be a mini pond. If you have a big building, you gotta have a big pond to let all the heat disperse around the water. Okay. How deep do we build the piping systems? You want to have a long loop of plastic tubing at the bottom of the lake. So you can have these, you can lay this at the bottom of the lake and you're gonna literally wrap a bunch of tubes around because you want more surface area. The more surface area the tube has, the easier it is to dissipate the heat or absorb the heat. Remember, this is a heat pump. So in the summer, we're going to take the cool water, the temperature, absorb it into the pipes, and pump that into the building to cool that building down. In the winter, the water is going to be warmer than the outside air, and we're going to pump the warm water, the heat from the water through the pipes into our complex. Okay. So it's just a large body of water is a stable temperature source, and we're just using it to our benefit. Okay. Lastly, we have an open loop system with 2 wells. So here, we're lucky enough that we built our building on top of a well water source. So there's underground water channels for us to use. And yeah, so where there are land requirements for a BLS heat pump, you have an underground source of water nearby. And you literally just build 2 pipes. You build one pipe with a filter, and you're just going to draw the cold water. You're going to physically draw that water into your building, and it's going to go through all your piping, and it'll cool your house down, and then it'll spit the warm water back into the well water, and it'll just cool back down. And you're just going to constantly pumping water in, and it's the same idea. This water is going to be constant 50 degrees Fahrenheit, and it will help stabilize the temperatures whenever it's really cold or really hot outside. Okay. So how deep do we build these piping systems? You need to pump and pipe. So the pump and the piping needs to be installed to pull water. So however deep this water well is, you need to go that far deep. It could be 50 meters, it could be 100 meters, right? Also, you need to install a return pipe to push the water back into the well as well. You also need to make sure they're a little farther apart. If you put the pipes right, if you put the inlet and outlet right next to each other, you're going to be pumping that warm water right back in. So you're going to have to space them apart so the warm water comes in and cools off, and before it goes back into the intake again. Okay. So if you notice, water is always a good medium for temperature control, right? We're just using it whenever we can. So those are your 4 or 5, 1, 2, 3, 4 different types of geothermal assisted heat pumps, and our conventional one we use for all of our houses. All right, so let's go ahead and shift gears. The last part of this chapter is we always got to talk about environmental impacts, right? We got a bunch of cool pros. Sounds so awesome right now, but there's always a catch. And the question is it a big catch, or is it something we can live with? So free heat's awesome, but we have environmental impacts we need to consider. Number 1 is air pollution. Number 2 is water pollution. Number 3 is land uses, because geothermal sites are really large. And number 4 is induced seismicity. So basically, there's many earthquakes that can happen because we're messing with the heat underground. We take too much heat out, the rocks will shift, and you'll have these little earthquakes that they can do some damage. Okay. Talk about each one by one detail. First one is air pollution. What type of pollution, air pollution, does geothermal energies produce? Small amounts of carbon dioxide, sulfur dioxide, and nitrous oxide in some form or fashion, right? Dioxide or some bigger, heavier elements. All three of these are common with coal-fired plants. Is basically you have fossil fuel in the ground. There's going to be small pockets of these minerals and these other elements. That's just part of the drilling process and just finding them naturally in the earth. When you put water into the ground and you pump it out and use it for electric generation, you will uncover and like dig up some of these small pollutants. It's just in the ground. You can't help it. Okay. Now, is it that big of a deal? Obviously, the air quality suffers when we release these into the air. No questions asked. But honestly, it's a minor effect. The reason why it's minor is you compare to fossil fuel, it's nothing. This is the whole output of a geothermal plant is equivalent to maybe 8% of what a coal plant puts out. Meaning it would take 12 geothermal sites of the same power capacity to equal one coal plant of pollution. So you're basically getting 11 times more power generation for the same amount of air pollution you're doing by going to geothermal. So yes, we're going to suffer a little bit, but it's not as bad as coal plant by a large margin, and we're probably okay with that. Okay. Water pollution. Well, remember, you're dumping a lot of water into a geothermal site, and that water spreads. Not all of it will come back into your well. It might spread elsewhere, right? So remember, what type of water pollution does geothermal energies produce? You will mix water with brine inside the well, and you'll make salt water. Okay, so you're pushing a lot of salt water and brine water through that can spread out and mix with the groundwater tables of the nearby area, because you might spread the water out a little farther than what naturally would have gone to, or the water would never been present and begin with. It was a dry rock formation. So you're adding water into the water table, and I don't know about you, I don't want to drink salt water out of the well. I doubt anybody does, right? That's also bad for the plants. Okay, so there's some issues with this. How can we, and so the question is, how do we keep water pollution in check? Well, in today's world, because we care about our environment a lot more, we put groundwater monitoring systems. Kind of like the guy has here, is around a geothermal site, maybe a couple miles out, you would drill deep and put a water pipe, and you will pull the water out of that area, and you'll have equipment to constantly test it to make sure that we're not putting too much salt water or other chemicals in the surrounding water. So basically take your geothermal site, surrounded by a bunch of monitors to make sure the water stays contained. Okay. Additionally, I will go to the houses nearby the residential areas within a 10-mile radius, and I would look at their drinking water out their faucet and run some tests to make sure that the water is acceptable, purified level. Okay. If it gets a little too dirty, that's probably our fault. We need to go fix something. Okay. Next is land use. Geothermal sites like this, they're pretty big. That's a lot of area that could be used for something else. So what do we mean when we say land use is environmental concern? This land use takes up a lot of space. Could be used for other industries like farming, raising cows, even other plants, or even neighborhoods. Okay, so you always ask yourself, if this land is in the middle of nowhere and nothing's nearby, sure, there's not an issue. But would you build a geothermal site in downtown LA? Probably not, because it's not worth it. See, that's where the land use comes in. The question of it. Okay. How is this compared to other electric generation sources? With geothermal sites, have less land usage than solar PV plants. So let's say this is a 300 megawatt geothermal plant. The PV's plant equivalent, a 300 megawatt PV plant, will be 10 or 20 times larger than this land area wise. So it definitely wins over solar. But this uses more space than a fossil fuel plant. Fossil fuel plants are very compact. Right? That's why people like them. And so that's the kind of trade-off we take. So honestly, geothermal is kind of in the middle. It is definitely bigger than traditional fossil plants, but it's much less than solar plants. I think I could live with that, middle ground. Lastly, we got induced seismicity. This is basically a fancy word to say earthquakes. Mini earthquakes, to be exact. When we constantly remove heat from the rock and we inject water, we will change the shape and size periodically of the rock bed itself. When we're taking heat, things shrink, right? So if you do it enough at a large scale, you can shift the ground layers. Literally, the rock bed underneath could shift like a few inches to the left or the right or up or down. As you shift a little bit, you're going to cause a little mini earthquakes everywhere. Okay? It's not going to be huge, but you will shift things and then it'll propagate outwards from your site. And if you have a town nearby, they might feel that earthquake. Okay. So what you have to do is, you have a geothermal plant, you're doing a bunch of water injections, changing the temperature. You might see how we might break this rock layer and it might shift a little bit. That sudden shift will cause seismic activity and vibration waves, and it will hit this town. So what we could do is we put ground monitoring systems to check to make sure these earthquakes, when they happen, are not that big. Okay. I think it's inevitable you won't have seismic activity, but as long as it's not big enough to damage houses and homes, I think you'll be okay. Okay. How does it affect nearby area and local population? Obviously, the big thing is structural damage to buildings, roadways. We want to make sure that never happens or minimize it as much as possible. So that's kind of the big scare people talk about. Honestly, this is not that big of a deal. As long as you do geothermal sites in remote areas, you're not going to see much of an issue. It's if you install this in the downtown area, that's when I'll be more concerned. Okay. So overall pros and cons for geothermal as we wrap up this week. Big advantages of geothermal power generation are it's a great source for producing electric energy because it runs like a fossil plant. Very standard steam turbine generator, lots of inertia, very stable for a system, runs 24 hours a day. This is the most ideal generation source from a power grid operation standpoint that we have. Okay, don't need batteries, don't need weather profiles, none of that stuff. Okay, it's a sustainable heat source because as long as we use it at an acceptable rate, the heat should always come back from the core, reheating the rocks that we're taking the heat from. So we know a rate of how fast the heat will replenish. We take out the same rate, we'll keep that same heat forever. Lastly, overall, it's minimal air pollution. It does have some, but compared to fossil plants, it's nothing. I say that's overall. For something that behaves very close to a fossil plant, we don't have the big con of air pollution. This is a good advantage, in my opinion. The big disadvantages for geothermal sites is it's very expensive capital startup cost-wise. So when we want to install a plant, we have to do a lot of drilling, like really deep in the earth, make lots of wells. Drilling is very, very expensive. So as long as you can eat that $100, $200, $300 million cost of getting the drilling done and building the plant, everything afterwards is gravy. It's good. But that people don't like just dumping $300 million for a project. That's the hard part. So it's very expensive startup cost. It's location dependent, right? You have to figure out where to get to do surveying to see where the geothermal sites that we can use. And then we have to build a plant there. Okay. And it could be in a very bad spot and we don't do it, right? Oh, another one is water pollution. You're messing with the water tables, the drinking water tables nearby. You could mess up people's water out their faucet. You can mess up the plant life nearby. You can mess up the farms and the crops. There's some issues with water pollution you gotta always keep track of. Lastly, we have seismic activity that can happen to damage buildings. This is really rare as long as we're not doing too much invasive things. It shouldn't happen, but you should be ready because it could happen. Okay. Ultimate review for geothermal sites. I think if the location that we have to build a plant, if that location is near a city or a nearby transmission line for us to hook up to, we should use it. If it's 150 miles from the nearest power station or city, it's not worth the cost of building the transmission line to it to get the power under the grid. That doesn't make any sense. But if it's 4 miles away from a city or a transmission grid, a substation to hook up to, that's not that bad. I build it. Okay. So that's the big take at the end of the day. So overall, of all the renewable energy sources, I think geothermal is one of the best ones you could use. So summary, put everything here, geothermal applications and concerns. What are the practical uses for low temperature geothermal sources? Again, space heating, so heating our homes, cooling our homes, melting snows, hot spring spas, greenhouse and aquaculture heating for the fish and the plants. Anything that helps stabilize the temperature to a constant level, we can use low temperature geothermal sites for. Okay. How does the heat pump utilize geothermal energy sources? You can use heat as a source for heating or a heat sink for cooling, right? So whether we need to warm, we have a cold house, we will warm up, we could use that to bring the heat towards us. If our house is too hot and we want to cool it down, we could just pump the heat into the geothermal site and get cool water out of it. So it always helps stabilize things. Excuse me. How do you calculate the coefficient of performance for a heat pump? COP is always equal to the heat provided versus the energy used by the system. It should be greater than 1, otherwise you should not be running the system. 5 is really good. 3 is pretty decent. 2 is 1 is turn off the system. Okay. What are environmental concerns for using geothermal power generation? We talked about air pollution, water pollution, land usage, and induced seismicity. Right. So as long as you're okay with all those, I'm okay with all those. We should start building these wherever we can. Okay. So that's all I have for this week. Thanks for showing up and listening to Geothermal Power Generation site. So lecture. So hope you guys have a good week. We'll come back next week and start something new. So, other than that, catch you later. See you around.